Good morning. We're back here to the CSE 455 Software Engineering lecture um, for spring 2020. Our meeting today is the 2nd of June, Monday. Um, Let me start with deadlines. We have completed reviews of all software architecture and design. And if you'd like to revise your SAD, it will be accepted on the finals day, but you should include additional um, design for prototype number two. And I will review it again and for partial credit for those who want to resubmit. Okay? So that will be finals day, the 10th of June. Retest of prototype 1 was done last Friday, 29th of May. So team should have received a revised test report from the QA team. So you should have talked with the QA team last time and arrange for a retest. So I will review again the QA team test reports. Performance evaluation of the management team consisting of the project manager, assistant project manager, and the team lead, and also all the team members of a team were evaluated. Deadline was last 29th of May also. And I will give you copies of your evaluation. So I will individually send you your evaluations through Slack, um, the Slack channel, direct channel from Dr. Concepcion. Okay, and then the final requirement, which is QA testing and delivery of iteration number 2 of prototype number 2. Deadline is the finals day, the 10th of June. So we are coming to a close for software engineering this spring. Okay? Um, Let me continue my lecture about testing. And we were talking about white box testing before. And white box testing, re- uh, reviewing you, white box testing are choosing test cases that would exercise the path in your um, uh, segment, function, or class. So the testing that we do for white box is we know the internal structure of the program, and therefore our aim is to exercise the different path in the program by choosing test cases that would uh, execute those paths at least once. Okay, uh, um, and um, anything that or any information about the internal structure when you are choosing test cases, that's white box testing. You know what is inside the program, and therefore you're exercising the path through the program. Okay? So here we have another branch testing. It is called testing the branches. So we often have a condition, compound condition, with an expression, a relative operator, a relational operator, and an E2. So we need to have 3 test cases at least to guarantee the determination of the relational operator error. So you should have a test case where E1 is greater than E2, or E1 is less than E2, or if it is included in the relational operator, E1 is equal to E2. So test all possibilities of true or false branches through this condition. And I think that is standard practice as we have seen before. Okay? All right. Now, next one is domain testing, white box also. This requires 3 or 4 tests to be derived for a relational expression. So the expression that you see over here is may not be numeric values you are comparing. It could be maybe positional or maybe weights. So that's domain, which is specific with the program domain of the program. So E1 will have a value that could be maybe alphabetically positioned, and we have a relational operator that is going to test whether E1 is greater than, equal to, or not equal to, and so on. We should have 3 or 4 test cases for that. And if it is Boolean, the expression evaluates to a specific value. So there are n variables that are Boolean. So all of the 2 to the n possible tests are required. So let us say you have 3 variables, each of which will have a value of true and false. So that's going to be 2 to the 3, and 2 to the 3 is the number of combinations of 3 variables having true or false each variable. Okay, so that would be the test cases that you will try. Okay, so that is for Boolean expression with n variables, 2 to the n possible tests are required. So if there are 3 variables, as I said, and each one will have true or false, you have 8 combinations. You have 4 variables, you will have 2 to the 4th. Okay? And of course, as they grow bigger, that will be more and more test cases to use. Now, the black box testing is one where we don't know what is inside the function, how the program is structured. That means we don't know the branches, we don't know the loops. All we know is the specified function that it's supposed to do. So what we are testing is the function. Is the function operational? Is the function functioning correctly? So that's black box testing. So again, comparing white box to white box testing, white box is one where we um, um, know the structure of the program, and therefore our test cases are driven by exercising each path in the program at least once. That is given through a measurement called cyclomatic complexity. So if we know the path inside the program, we exercise it at least once. Okay? Black box testing, I don't care what's inside the program. All I know is that you give it a set of inputs, a set of outputs comes out, right? And it is supposed to be performing a particular function. So we are testing whether the function is correctly executed. Okay, so that's the difference between white box and black box testing. So we're going to talk about different techniques of choosing test cases for black box testing. All right. So here is kind of a um, general idea of finding errors in black box testing. So it is a function. So of course we must find out if uh, the function is incorrect or there are missing function. So incorrect means you have a function that is um, missing, or it is not. Of course, how can you test a missing function? Yeah, that's kind of weird. But incorrect function, yeah, you can test that. Now, missing function can be determined actually through review. Okay, so you have a review of your architecture to find out whether all the use case that you have specified in the SRS are actually implemented. So that's how you um, determine missing functions. Okay, but of course we can't determine missing function. It is as if you are asking a class, those who are absent, please raise your hand. Okay, we can't do that. So incorrect function, yeah, we can test for that. Okay, missing functions, we have to go back to our software requirement spec and apply sequence diagram to determine if we have um, specified all the functions that is required by the client. Okay? Interface errors. Now, the interface consists of parameters being sent from one function to another. So sometimes we make the mistake of the order is different, and therefore that makes a lot of difference. If the order of the parameters doesn't match the parameters of the function being called, of course, the function will not perform. So, but most of the errors are in the interface error. So you check interface errors. Third one is errors in data structures or external database access. So the data structures, the way you manipulate the data structure may be in error, and therefore it will not function correctly. Like, I don't know, maybe linked list uh, and versus array. Okay, so you um, make a mistake about assumptions in the data structure that you are calling of the module you are calling, and if you have a um, misconception about the data structures being used, uh, that could create an error. Like, yeah, most common, like an array, you exceeded, you have a over the bounds of the array, thinking there's one more, but actually there is none. So that could be that could produce errors too. So data structures and databases, okay, and databases are also source of error because you assume certain things in the database. You are calling a table, but that table is not present, or you are accessing a data that is not there on the database. It will produce an error. So make sure you check those. Okay. Performance errors. Performance errors. You promise 2 to 3 seconds. Now, if it is more than that, then there is problem in performance. And performance is important in execution because you don't want the user to wait for a um, a unreasonable long time to get the result. And the other source of error is initialization. You forgot to initialize. Okay, so what happened? The whatever was in that variable, like garbage, you will work with garbage, and therefore a program will not function correctly. And termination errors. There is no um, uh, correct way of terminating a loop, so you have what we call an infinite loop, which is a common problem in recursion. And recursion is a powerful um, um, mechanism in solving problems, but if your termination is not correctly done, it will not perform properly. Okay? All right. So we derive a set of test cases that satisfy the following criteria. So what we are talking about here in black box testing, you want test cases that would reduce the number of additional test cases that must be designed to achieve reasonable testing. Um, Remember, we cannot do 100% test case running. Although, as I said, there are automated test cases generators nowadays, but still, if the input is high, that means the number of input is high. Sometimes test case generators may not be um, enough to do that. Like for instance, compiler. Okay? How can you do a test generator for compilers? The input to compilers is any set of program that is written following the grammar of the language. How many kinds of input, different programs can you think that the compiler can handle? We cannot actually use 100% test case because the different kinds of program the compiler will read is infinite. There is no limit. So test case generators will not work for that. Okay. The next one is test cases that tell us something about the presence or absence of classes of error. We want to determine classes of errors that are eliminated because that coverage covers all possible errors in that class. So if we are able to determine test case that identifies a class of error, we will eliminate everything in that class of error that might occur. And so we don't want test case that will only satisfy a specific test at the hand. Okay, so we want to determine classes of errors that if we have a representative from that classes of error, we don't need to test every element or every item in that class. Okay? All right. So um, let's talk about the principle of equivalence partitioning. So we talk about classes of errors. So what is equivalence partitioning is the dividing the input domain into classes of data from which test case can be derived. And also, once we find the equivalence class, we those classes represent a set of valid or invalid state for input condition. Let me show you example of that. I mean a representative of that. So if we have all the error, I mean all the data that you can think of as test case for this program, what we want to do is to determine a, uh, a member of class A. I mean, if we can determine the classes or equivalence classes of inputs to this program, and we identify a test case here in class A, that means I don't have to test all the elements of class A because that particular element that I found out represent class A errors. So that's a good test case. So if we can partition all the inputs to the program and determine uh, uh, equivalence classes, we can select uh, um, a, uh, a test case within a class, and that should be sufficient to uh, to assume that any other element of input in the class B would have been represented by that specific item that I have selected for class B. And you can also think that outside of these equivalence classes, anything outside of that are invalid test case, and they should not uh, be a valid input to the program. But remember, the cause of problems of programs is um, having to deal with invalid data. Okay, so um, that's the principle of uh, uh, the principle of equivalence partitioning. Okay, all right. So we have um, the errors um, for 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 black box testing. Here are the following categories for that. If the input uh, condition, oh, by the way, did I miss something here? Let me go back. Okay, I think I did that part there. Okay, so if the input condition specifies a range, then we should choose one valid and 2 invalid equivalence, okay, classes. So 1 valid, if it is a range, 1 valid and 2 invalid equivalence class. Let me show you that. So here, if you have this range, let's say the range is from X to Y, 3 test cases should be sufficient. One is, 2 of them are invalid, right here, less than or left to the left of X and to the right of Y, and 1 valid, which is between X and Y. Okay, so that's what a range is for. Okay. Next one is the if input condition requires a specific value, just one value, then we select 1 valid and 2 invalid equivalence classes are defined. Okay, so a specific value, 1 valid and 1 that is invalid, 2 valid and 2 invalid, 1 valid and 2 invalid equivalence class. If input condition specifies a member of a set, so we have a set, 1 valid and 1 invalid equivalence class are defined. Okay, and if an input condition is Boolean, 1 valid and 1 invalid class is defined. Okay, so that's the errors in this category. Okay, let me go back there again. Let me show you those examples here. Okay. Oh, I think I jumped the gun. It should be. Okay. So here are the test case examples for equivalence classes and boundary value. Boundary value, you have an X and Y, and you want to select 1 valid value between X and Y, and the invalid are outside or less than X or greater than Y. Okay, so here are the test cases that I will try for a particular program that it's inputting records, and the maximum records it can take is 16,383 records. Okay, so that's the maximum. All right, and so here test case, that means 0 records, means you're entering a file with no records. I mean empty record. So that is zero records and see how the program behaves for a null file. Of course, it should come back with a, um, a result that says, hey, the file is empty, I cannot process this. Or it is exactly one record, so that's the boundary value. Exactly one record more than the boundary of one record, two records. Some member of the class, the equivalence class 2, 723 records. Um, Within the boundary value, 16,382, which is one less than the maximum, and the maximum value plus one over the maximum boundary value. So you select test cases that are um, um within the value uh, x and y, and values that are outside of x and y. Okay? Let me go back to the transparency. Let me cancel that. Okay. Next one is we talk about boundary value analysis. That is, if an input condition has a range of x and y, we design values that are x and y just above and just below of x and y respectively. You should also have a input condition that is uh, the minimum and the maximum value, and apply the above guidelines to output conditions as well. Okay, so not only input, but we also check the output range as well. And if internal programs have um, been prescribed, um, here we should be able to design test cases um, to exercise the data structure at each boundary. Okay? Okay? Now let's look at this again. So uh, the range that I was talking to you about is a X and Y. Select outside of the boundaries. Select one that is inside the boundary. Exactly the boundary itself, X and Y. A little less, one less than X and one more than X. Here, one more less than Y and uh, one more um, unit than Y. Okay, and this test case, we talk about that, illustrating the boundary value. Now, let's have a sample black box testing for sample one, and this is actually um, a input to a kind of a banking function, and you're inputting, let us say, or maybe a manufacturing, and you're inputting item number. You're looking for a certain item number. Okay, and so if the item number consists of numeric only, you should have a test case that includes that has character instead of integer. Of course, an error, the program should return error. Let's say exactly 12 digits is the normal um, number of digits in a item number. You input less than 12. Oh, this is acceptable. So the maximum number of digits in your input is 12. So if you input less than 12, it should be okay. Exactly 12 should be okay. But if you input more than 12 digits, there should be an error saying too many digits. So those are what we call equivalence classes. So we divide the input into invalid input and valid inputs. Now, supposing um, you input an item name. So the item name is required, and if the item name should begin with a numeric, then input an item name that is the first character is not alphabetic, alpha character. So that should be an error. Less than one character, that should be an error. Actually, I don't know if you can put less than a character input, okay? But maybe, um, uh, I don't know, maybe you just press um, the enter key and there was no input at all. So that should be an error. One character, still acceptable. Between 1 to 25, so here 25 characters is the maximum. So between 1 and 25, it's acceptable. Exactly 25, acceptable. And more than 25, it is not acceptable. So these are the test cases that you should try based on the equivalence classes of input. Okay. Now here is a function testing. So this is a banking application, and you want to um, add to the database of mortgages of adding a mortgage. That should be okay. Add an investment should be okay. Modify a mortgage, modify an investment, delete a mortgage, delete an investment, update operating expenses, compute funds to purchase house, print list of mortgages, and print list of investments. So these are the functions that should operate correctly, and that is being tested. But you should also include um, uh, bad input. Like for instance, attempt to add a mortgage that is already on file. Of course, that should return an error. Attempt to add an investment that is already on file. That should also return an error. Attempt to delete a mortgage that is not in the file. Delete an investment that is not on file. Attempt to modify a mortgage that is not on file. Modify an investment that is not on file. Delete twice a mortgage that is already on file. Delete twice an investment. Update each field of a mortgage twice and check that the second version is stored. Attempt to update each field of an investment twice and check that the second version is stored. And attempt to update operating expenses twice and check that the second version is stored. So not only that you will try valid test cases, but you should also include invalid test case. Okay? These are outside of the um, valid input. So that should be tested, and you should, the program should handle this without crashing. Okay? And here is a graph that kind of a um, kind of a flag the behavior of programs as you test it. This is time, and this is the probability of error, 0 to certainty 1. So as you are testing your program, if the number of faults keeps increasing, okay, that means more and more errors are being found. Okay, you will reach a point where the program is no good, and therefore time to stop testing, because the program has a lot of bugs, okay, lots of faults, and therefore there will come a time that it is useless to fix the error, because the probability you will find more errors is high as you increase the testing time. So there is a limit where you will decide um, testing should be stopped because more errors will be found. And that's usually the behavior of testing. If the program is bad, more errors will be found. So time to stop testing. Okay? All right. Done with the um, equivalence partitioning method of determining classes of input, and also for the boundary value analysis, where you divide the input into valid and invalid um, classes. So now let's talk about the summary of software testing that we do. We have the unit testing, and the unit testing is testing of uh, a segment or a function or even a class of, of code, and you are doing either a black box or a white box kind of testing. And in the black box, you are testing for the functionality of the unit, whether it is performing it properly, and the white box, where you are aware of the structure of the unit, and so the test case are driven by being able to go through the different path in that unit, and at least execute it at least once. So that's for unit testing. Now, for integration testing, we have units that has been tested already, and you are in the process of integrating um, each unit into larger pieces of software, like a module or a component. And that's where you um, combine the modules or components that has been unit tested, and therefore you are um, uh, building larger and larger components of the software. That's what you call integration testing. And here in the integration testing, uh, it's hard to use white box testing because the components are getting bigger and larger. So testing by following the path may not be feasible. And so black box testing is probably practical, is probably the kind of software testing that you're going to use in integration. And as you are integrating, you are building the system piece by piece. So if you integrate larger and larger components together, you will form the system, which is actually the software itself, running with other systems in the product. And therefore, system might include servers or database and other system that is necessary to run the application. So you're doing system testing. And here, definitely, you are using black box testing, the testing for the functionality of the system itself. And then the acceptance testing is the testing done at the client's environment. So if the software is being used in a bank, then it must be tested over in the bank, and the client will actually see the software being used in the bank, or a manufacturing system, or even a school. Like here at CSUSB, we are using a very large enterprise system that handles school records, financial systems, personnel records, physical facilities records, and everything. So they are all integrated together, and whether the system you have built will work properly with the other systems that exist. And that's what you call acceptance testing. So let me show you um, the a diagram about all this testing that I have spoken. So here is the unit testing, and the unit testing is a module or a segment or an object that is being tested separately from other modules. And the kind of testing that we are using here are testing for interface. Are the parameters being passed by the module correct? Positioning is correct. The data types are correct. And so that's the interface kind of error that you are looking for. Local data structures, are you not exceeding the bounds of your array, for instance? You have an out-of-bound array that could cause error. Boundary conditions, you have a range of values from X to Y. Are we testing boundary conditions? Um, right on the lowest boundary, the highest boundary, a little less than the lower boundary, or a little more than the upper boundary? Are you testing that? We are also using independent paths. So the independent path analysis is being sure that you are um, executing each path in the module at least once. That's the cyclomatic complexity measurement that we have talked before. And then error handling path, like input, we have an invalid input, the module shouldn't crash. It should actually handle that special case. So here the module is being tested by itself, not with other modules, but by itself, and you have test cases to actually try and verify that the module is running properly. Okay? So here is what happens if you like to test the module by itself with no other modules communicating with it. So we have a driver. So this is a module that you have written, and the sole purpose of the driver is simply calling the module that will be tested and pass to it all the test cases that you are trying. So interface test case, local data structure test case, boundary condition test cases, independent path test cases, and error handling test cases. So the module is being fed by input from the driver, and the driver is just a module that sends test cases to the module. Since the module is to be tested in isolation of other modules, so the driver function is simply to feed test cases to it. And if the module is supposed to call other modules, we build what we call stubs. And the stubs are also um, um, uh, temporary programs that the module pretends to call the stub, and the stub returns something if it is a more sophisticated stub, or simply just receives the call. So the stubs represent modules that the module to be tested are calling, and the driver is the representative of a module that calls this module to be tested. So the module to be tested is tested in isolation of other modules. This is called unit testing of the module. Okay? Now, let's look at those stubs and uh, and drivers. Okay, so the stubs, remember, are modules that is called by the module to be tested, and it could be as simple as displaying a trace of the message that it was called. So it could be a very dumb stub. Stub A just displays that it was called. Okay, or it could be a little bit more sophisticated than stub A, and stub B is pass a parameter. So the parameter is passed to stub B and displayed by the stub. So to review, remember, we are calling stubs by the module to be tested. We are pretending to call this stub, and the stub receives the call from the module to be tested. Okay? All right. So it could be just displaying the parameter that was passed, that's stub B, or a little bit more sophisticated, like returning a value from a lookup table. So the stub receives a value, and then a value is returned from a table, and the stub sends that back to the module to be tested. Or it could be very sophisticated, like stub B. It do a table search for the parameter that was received and return an associated output parameter. So instead of just returning a value from a table, the table actually contains um, uh, a more correct answer to the parameter that was passed, and it is done through a, um, a search and return, search for the input parameter, and for that input parameter, the associated output for that stub is returned. So you could be just building a very simple stub that just displays a message that it was called, to a stub D that accepts parameters, and through a search here, the correct parameter result is returned to the module to be tested. Okay? All right. Now, for the driver, the driver for a module to be tested, the driver could also be as simple as invoking a subordinate, so just calling the module to be tested, or the driver could be um, sending a parameter from a table or external file right here, and the driver could be receiving the result from the module to be tested to the driver, and the driver receives that, or the driver can send and receive result from the module to be tested here. So the driver could be less sophisticated as driver A, to a driver that sends a parameter and accepts a parameter return from the module to be tested. Okay? All right. Now, let's talk about integration testing. Okay? So, integration testing could be top-down, right here. That means the modules that we have tested individually using unit testing are now being integrated together one by one, or more than one at a time. And the module 1 is the very top module that is actually containing probably output screens to the user, and the lower modules perform the low-level operations. Okay. So from M1, we begin as far as we have integrated together. We begin top down here in this procedure, goes as far down as the lowest level. Okay. M1, M2, M3, M4, and M8. Okay. And then once the lowest level has been reached, you begin integrating M3, Um, and then M3, and then M7, maybe go as low here. And then from M1, you begin integrating M4 all the way to the lowest level. So top-down is a way to integrate the modules from the very highest module, highest level module, to the lowest level module. Okay? Top-down integration. And of course, bottom-up is integrated beginning from the bottom. Okay, and the bottom part was integrated together. So this is done in clusters. So cluster 1, cluster 2, and cluster 3. Now remember, the lower level modules actually perform the actual operation of the program, and you begin integrating from the bottom, like here, D1, D2, and D3 are the next modules to be integrated. And then the higher modules, MA and MB. And then finally, the highest module, MC, is integrated to form the system. This is called the bottom-up integration. Okay, and sometimes the bottom-up integration is kind of a disadvantage because you never see the output till you reach the top level. Okay, and so you are never sure whether the program is working without looking at the output, because you begin from the bottom level. Okay, and this kind of bottom-up integration to some projects could be better. To other projects, the top-down. But there are other projects that may not be conducive to strictly bottom-up and top-down, and so there is another approach called the sandwich approach. So like here, for instance, we can begin the cluster, okay? And while we're doing the cluster, we begin doing top-down, okay? We begin from the top-down, and then somewhere in the middle, they will meet, the lower level will meet with the upper level, and thereby producing the input-output that you have at the upper level. That's what you call sandwich approach. Okay. Okay. So that concludes the lessons for testing, and so I will continue my lecture on Wednesday, and talk about other things in software engineering that is relevant to your discipline. Okay? Be safe and healthy.